Thank you so much, Lance, and thanks, Fernando and Andrea, for all those glowing words. I hope I can live up to such a buildup. It's always a challenge when you get such a nice introduction. So I'm going to share my screen. Hopefully you can see just a single slide. So my talk tonight has this title, Commonwealth at Risk, Predicting and Preparing for the New Normal. And as you heard Lance just describing, global change, global climate change is something that's on everybody's agenda, but not everybody really understands completely what it means. And this notion that we're talking about global change often immediately makes people ask the question, what does it mean for me? What does it mean in my community? What does it mean here in Virginia? So I'm going to try to give you literally a global eye view of how climate change may be affecting the Commonwealth of Virginia as we go forward. And since somebody pointed out it's April Fool's Day, I didn't want to start with a joke, but I will refer to one of America's greatest humorists, Mark Twain, who said, everybody talks about the weather, but nobody does anything about it. And of course, it's an April Fool's joke because he isn't the one who said it. It was this fellow, Charles Dudley Warner, who actually should get credit for this quote. But it's even more of an April Fool's joke on all of us, because in reality, we are all inadvertently doing something about the weather. We're changing the weather. When we talk about global climate, that's the statistics of weather, basically what we expect to happen on any given day. And that's undeniably changing. It's changing worldwide. It's also changing regionally and locally. And it's because human activities, particularly since the Industrial Revolution and an accelerated pace in the past 60 years or so, is changing climate. So we're going to try to dig down into that and try to understand a little better. The way I like to organize our communication of this, I rely on my colleague here at Mason in the communications department, Ed Maybach, who points out that the essence of effective communication is simple, clear messages repeated often by trusted sources. Well, you don't know me, so you don't necessarily have to trust me. But I'm going to try to convince you that the data we have and the understanding we have of the Earth's climate system will help you understand the whole situation. And Ed breaks down the problem of climate change communication into these four very simple messages. Climate is changing. We, humans, are responsible. The consequences are serious, and there is hope. Well, from a scientist's point of view, these messages are great, but they are a little bit overly simplified. And so we tend to think of these in a little bit more detail. So when we ask the question, how is climate changing? We have data to show the climate is changing today faster than it has at any time in the past 2 million years. And so, of course, the students in our Ph.D. program in climate dynamics, we're constantly asking them to explain to us why that's happening. We are responsible. Well, who's we? Well, we happens to be humans who burn fossil fuel or who alter the natural landscape. So land use change, cutting down forests and so on. And the scientific question is, well, how does that work? And quantitatively, how much is the change that humans are responsible for? This third point about the consequences are serious. Well, on balance, there are both positive and negative consequences of climate change, but on balance, there are more negative impacts than positive ones. And so we have to prepare. And this notion that there is hope, well, absolutely there's hope. We already, in the words of so many of those science fiction movies you've seen, we have the technology. So we really can address the issues of climate change, but it's a challenge. And it is going to take concerted effort by everybody in our society. And of course, part of what we try to do at Mason is answer this last question. How can we solve this problem? So let me give you a little bit of deeper understanding of each of these 4 points. Climate is changing and we are responsible. Well, this is the Earth's climate in a nutshell. And by the way, a lot of the material I'm going to use as visuals for this talk are taken from a course that Professor Shukla in our department and I teach that's called Climate 101. It's a semester-long course we offer every fall. And it's usually very well attended. It's a so-called Mason core course, and it's open to seniors. We also allow citizens from the community to come in and monitor the class. So if you want to learn more, that's a shameless plug from my class, Climate 101. What this diagram is showing you is how the Earth's climate works. So we get all of our energy primarily from the sun, and the sun beams that energy towards the Earth through our atmosphere. Now, happily for us, the composition of our atmosphere is such that most of the energy coming from the sun passes through. Some of the dangerous energy, the ultraviolet rays from the sun, are filtered by the atmosphere. But for the most part, most of it gets all the way to the surface. The surface warms up in response to that energy and emits energy back outwards towards space. But there again, the atmosphere now has a role to play because the atmosphere is largely opaque to the energy that's flowing out from the surface of the Earth. And we refer to this effect as the greenhouse effect because it operates very similarly to the way a greenhouse keeps the plants warm. It's basically shielding the plants from the wind, which would be taking the heat away from the plants. And it's also keeping a lot of that infrared radiation that's coming up from the surface, from the soil. It's keeping that from escaping into the atmosphere. So if you think about this greenhouse effect, we can do thought experiments, and we do this in our classes at Mason. We could take the atmosphere away and ask, what would the Earth be like in that case? Well, without the greenhouse effect, the planet's average temperature would be about 18 degrees below the freezing point of water on the centigrade scale, or it would be 0 degrees Fahrenheit. It's not a hospitable planet if we don't have an atmosphere. Of course, it's really hard to breathe if you don't have an atmosphere, but it's also so cold that water is largely frozen. So we have no liquid or vapor forms of water on the planet in that case. With the greenhouse effect, the average temperature of our planet is about 15 degrees above the freezing point of water on the Celsius scale, or about 59 degrees Fahrenheit. So you may not realize that the temperature of the planet is 59 degrees, but that's an annual averaged over the whole planet's surface. So including the Arctic and the Antarctic, which are very, very cold, and the tropics, which are very, very warm. And the main constituents of the atmosphere that contribute to this greenhouse effect are these chemical formulas down here at the bottom of my slide. I'll just mention these are water vapor, so water in its gaseous form, carbon dioxide, methane, nitrous oxide, ozone, and sulfur hexafluoride, among others. And these gases occur in very small amounts. You probably are aware that our atmosphere is primarily nitrogen, and the second most plentiful gas in our atmosphere is oxygen, which of course is good for organisms like us. But at the trace level, at the couple of percent or smaller volumes, smaller concentrations, we have water vapor, carbon dioxide at about 400 parts per million, methane at a few hundred parts per billion, and so on down the line. So it's just these very tiny concentrations of gases that are giving us this greenhouse effect. Now, as it turns out, if we change the concentrations of those tiny traces, and because the amounts of the greenhouse gases, those gases that give us that warming effect, are so small, it doesn't take a lot to change those trace amounts. So here's a chart, and it's a little complicated, so I'll explain it slowly. This is what we call a time series from the year 1750 to near the present. And what we're showing on this chart is this fairly esoteric quantity that's effective radiative forcing. It's basically telling us how much above, if we're above the zero line, or how much below, if we're below the zero line, we are changing the balance of energy between the energy we receive from the sun and the energy that the Earth re-emits back into space. And so you can see on this chart, if we go back into the 18th century, we're right near a balance with occasional, these very sharp downward spikes, which I'll explain in a second. But then over time, since the early 19th century and then accelerating into the middle and late 20th century, you see this imbalance forming. And particularly this gray area here, that is the carbon dioxide contribution to the greenhouse effect. So as carbon dioxide concentration increases in the atmosphere, it causes an imbalance in the atmosphere, in the energy between the sun and the Earth. Similarly, we see the other greenhouse gases here in this light green and dark green colors. And then there are other things that are in our atmosphere that are interfering with that greenhouse effect and actually giving us a negative contribution to the energy balance. So here in red, we're showing aerosols, which are very tiny microscopic particles that reflect sunlight before it can warm up the surface. And I also mentioned land use. Land use actually can go either way in terms of warming or cooling. And on this chart, it's a net cooling. Then about these spikes. So every so often you see these very big spikes. These are large volcanic eruptions that project an enormous amount of aerosol into the atmosphere and essentially act like a parasol. They shield the Earth from the energy from the sun, and they cool the planet. They cool the planet quite a lot, but only for a very short time because the tiny aerosols that come out of the volcanoes eventually precipitate out. So the net effect of all of that is this dotted red line here, which is the change in our energy equilibrium that would be there if it weren't for humans adding carbon dioxide to the atmosphere and other greenhouse gases. So these human activities have increased this effective radiative forcing by more than 2 watts per square meter. And that's mostly, as you can see in the gray, due to carbon dioxide emissions. We projected in the future, if humans continue to emit carbon dioxide and methane and other trace gases into the atmosphere, basically what we call a business as usual scenario, we project that we could reach up to 8.5 watts per square meter of imbalance by the end of this century. Now, what do those numbers mean? What are 2 watts and 8.5 watts? Well, and I forgot to mention that all of this data I'm showing you comes from a government report. It's called the Climate Science Special Report. It came out a few years ago, and I highlighted here it's a Trump administration report because just to make the point that whether you're a liberal or a conservative, this data is the same, and the way that it gets presented has to be presented in a scientific format completely objectively. So what do we mean by these numbers, 2 watts per square meter? So 2 watts per square meter means that every small area, which is 1 meter by 1 meter, or about 3 feet on a side, is gaining an extra 2 watts of energy all the time. So if you multiply that by the surface area of the Earth, that's about 1 million gigawatts for the Earth as a whole. And that's equivalent to adding 40,000 of the largest hydroelectric dams in the world. It's also equivalent to putting a household light bulb over every patch that's 20 feet by 20 feet on the entire planet. So even though it sounds like a very small number, 2 watts per square meter, it turns out it can be quite a lot of energy imbalance. Now, where does that CO2 come from? Well, here we have a chart showing us again a time series now from the early or middle of the 19th century to the present. And here you can see where this carbon dioxide sources and the sinks, where it comes from and where it goes. So as you can see, since about 1950 or so, there's been an enormous acceleration of the concentration of the emissions of carbon dioxide from the surface. And that's primarily by combusting fossil fuels. Fossil fuels are things like petroleum and natural gas and coal. We call them fossil fuels because they were formed at the same time as the dinosaurs were living on Earth, many hundreds of millions of years ago, or tens to hundreds of millions of years ago. And so as we excavate that fuel from the ground, we call it fossil fuel. It's associated with fossils. Well, that fossil fuel combustion, you can see, is the main contributor to carbon dioxide over the past century or so. And land use change has likewise been a contributor to carbon dioxide, primarily because trees act as sinks of carbon dioxide. Trees absorb carbon dioxide from the atmosphere for photosynthesis, and they fix that carbon in their stems and trunks. So as we mow down forests to make room for settlements and for grazing land for animals, we are removing the trees that could otherwise be absorbing carbon from the atmosphere. If you look below this horizontal black line, you see where that carbon dioxide is winding up. And about half of it is winding up in the atmosphere because carbon dioxide is not particularly reactive chemically. So once it gets into the atmosphere, it can stay there for a very long time. About half of the rest is being absorbed by the ocean. And this is another whole set of issues that are associated with carbon dioxide emission, because as carbon dioxide is being absorbed in the ocean, it's decreasing the pH or increasing the acidity of the ocean. As a result of dissolving the carbon dioxide in water, you get a weak solution of carbonic acid. So we're transforming our oceans from very alkaline water into a weak solution of carbonic acid, which has its consequences for the organisms that depend on the pH being very stable. The other half of the remaining carbon dioxide is being absorbed by the land. So you see this getting larger, this green area growing in time. And that's because a lot of the deforestation that took place in the 19th century for agriculture and for building settlements is now being restored to forest land. So we're seeing a restoration of some of that carbon dioxide absorption by the land surface. So now, where is that carbon due to combustion coming from? Well, now we're looking at another time series, but just a very short one, just since the middle of the 20th century, the past 70 years or so. And here you see the global uptick in global emissions of carbon dioxide. Down at the bottom, on the left-hand side, you see which fossil fuels we're combusting that are producing that uptick in the emissions. And you see at the beginning of, in the middle of the 20th century, it was primarily oil and coal that were producing most of these emissions. And over time, oil has gone up and down. There's the oil embargo is in this period in here. But coal had a tremendous uptick at the beginning of the current century and then flattened out in the mid-2000s, mid-2010s. Meanwhile, natural gas has been sort of inexorably increasing. And a large part of this uptick at the end here is a result of technology. We're now much more efficient at getting natural gas out of the ground through a process called fracking. So you see the increase in natural gas emissions. And then on the right, you can see a breakdown in the upper right here. You can see a breakdown by countries. So at the beginning of this time series, the United States was king, was the biggest emitter on the planet, and has remained roughly constant since about the year 2000, or actually declined a bit. Meanwhile, the developing countries, China in particular, and also India, have gone through tremendous industrialization the last couple of decades. And so China has now eclipsed the United States, as well as the European Union, which is this light blue curve. And India is rapidly growing as well. So we can see the geopolitical nature of this problem as well as the scientific one. So how do we know that the carbon dioxide we find in the atmosphere is coming from fossil fuel combustion? Well, that's one of the wonderful things about science, is that we can actually measure what's going on in our atmosphere. And we have these various indicators that in this cartoon, they're referred to as fingerprints on climate change. But some of the things we might consider as an alternative explanation compared to fossil fuel combustion and increasing carbon dioxide concentration as the perpetrator of the global warming. You might say, well, maybe the sun is increasing the output of energy, or you might imagine that there are other causes. Well, all of these characteristics that we have observed, the fact that there is less energy actually escaping from the Earth into space, the fact that the stratosphere, which is the upper part of the atmosphere, is cooling versus warming near the surface, the fact that when we measure the carbon that we find in coral, or when we measure the carbon that we find in the carbon dioxide in the atmosphere, we find that those are coming from fossil fuel combustion sources based on an isotopic analysis. Also, we know that the nights are warming faster than the days are, and that's a good indicator why it's not the sun that is causing the change. It's the fact that we're not letting as much energy back into space as we used to. And so here's what the cause of all of that increase in carbon dioxide in the atmosphere is: warming our planet, as we expect it to, because we've changed the equilibrium, the energy equilibrium of the planet. So this is another one of these lovely time series on the left from the late 19th century to the present, showing you the global average surface temperature basically going up unabated with minor small changes along the way. And here's how that breaks down in terms of spatial distribution. You see most of the warming is happening on the continents, the warming is not as fast over the oceans. And what you can't see on this diagram because it's grayed out for data purposes, but the Arctic is actually warming about twice as fast as the rest of the planet is as a whole. So now coming to the second point, consequences are serious. So what? I mean, let's look at this picture again. This whole change from the late 19th century to the present of the global average temperature is all of 1.1, 1.2 degrees centigrade, maybe 2 degrees Fahrenheit. So it's probably cooled off by more than 2 degrees Fahrenheit since I started speaking to you. And of course, the Nats game is canceled tonight because it's too cold to play baseball. So why are we breaking out in a sweat over 1 degree centigrade or a couple degrees Fahrenheit? Well, the answer to that is a bit complicated, but it's relatively easy to understand if we break it down. So first, the fact that the average temperature is going up is accompanied by the fact that record high temperatures are also becoming more frequent and more intense. And I'm going to skip this diagram because it's a little bit complicated. I'm just going to show you an animation. So where you see yellow dots on this diagram, this is for the summer of 2018. So where you see yellow dots on this diagram, it was one of the top 5 warmest days at that location. And where you see a red dot on this map, it's a place where the daily record high was broken that day. Where you see these more crimson dots from time to time, that means the monthly average temperature at that place broke its all-time high. And occasionally you may see a black dot, like we just saw a black dot down here in the Gulf of Guinea. Those are places that broke the all-time record high ever. So clearly what we're seeing is an enormous increase in record high temperatures. And as it says down here at the bottom, people can get accustomed to a broad range of temperatures. But when the temperatures break the daily high or when the monthly record is broken, people get sick because they're not acclimated to the temperatures that they are experiencing. Here's another consequence of things warming up and getting drier. You saw last summer, the Western United States had a record high forest fire season. And it was the last in a series of every year breaking the previous record of how many and how intense the forest fires were. And it wasn't just here in the US. Last year also was a year of record forest fires in Australia. This is in the state of New South Wales, which is in the southeastern corner of Australia. And you see from satellite, you can actually see from satellite images, the plumes of smoke from all the forest fires in New South Wales. And if you were following the news at that time, you saw images like this, with kangaroos hopping in front of infernos as domiciles were burning to the ground. And another aspect of global warming is it's not just the warming, because the atmosphere is warmer. It has a higher capacity to hold water vapor. And when we combine high temperatures and high humidities, we get very dangerous conditions. So this is just data from India and Bangladesh, as you can see on this diagram. And where you see these colors, these orange and red colors, this is from historical data, meaning this is what we have observed in the recent past. We see temperatures of a quantity we call the wet bulb temperature, which is a combination of temperature and humidity. It's sort of like heat index or other measures that you've heard for combining temperature and humidity. You see that even in our current climate, we see these wet bulb temperatures reaching the 30s and 30, 31, 32 in the centigrade scale. These other two diagrams are projections for the future. If you just look at this right-hand diagram, this is what we call the business as usual scenario. So that by the end of this century, we would see huge swaths of northern India, Bangladesh, and along the Bay of Bengal coastline, which would essentially become uninhabitable because the daily wet bulb temperature exceeds what a human can survive. So no humans would actually be able to go outdoors in this situation. Along with temperature and humidity comes rain. And this is part of the problem that my friend Ed Maybach, talking about communicating climate change, faces, because it's a complicated message. The rainfall change associated with global warming is both higher rainfall and lower rainfall. And we see this even here in the United States. So this is one metric of rainfall. It's the number of 5-year, 2-day events. It's just looking at ways of measuring extreme rainfall. And you see here in the northeastern United States or in the southeastern United States, basically everywhere east of the Mississippi, we've seen increases of 50 to 100% in the number of these extreme rainfall events. Meanwhile, we've seen a decrease in those sorts of events in the Southwest. And in fact, we see a higher prevalence of drought in the Southwestern United States. So it's a bit of a complicated message. Global warming is giving us both inundation, heavy rainfall events, and drought. We also see this happening where we don't project tropical cyclones to become more frequent necessarily, but we do project them to become more intense. And here's just an example, and I don't want to give anyone the wrong impression. We're not saying that Hurricane Laura from last summer was the result of climate change, but the fact that it was able to achieve such a high intensity, it was the strongest hurricane ever to make landfall in Louisiana. That's a consequence of climate change because it was the warm ocean temperatures and the high humidities available to provide energy for this system over the Gulf of Mexico that made it possible for this system to grow to such intensity. Other things that are happening because the Earth is warming, we're seeing ice disappearing. We're seeing the ice in glaciers on high elevations retreating. If you've ever been to Glacier National Park in the United States, that's wonderful. But your children, or certainly your grandchildren, if they go to a place that's called Glacier National Park, they won't see a glacier. And maybe that's just a tourist issue, but there are real consequences of ice disappearing. For example, here's a positive consequence. As ice that's floating in the ocean, the Arctic, disappears, it becomes navigable. So we could see freighters actually navigating through the Arctic and making it much cheaper to get TVs from Korea to New York City. But we also see this one. This is the Antarctic ice sheet. The Antarctic ice sheet is a very delicate system of ice that is flowing off of the transantarctic mountains into the Ross Sea and the Weddell Sea. And these ice sheets are very long and very thin, and they are subject to breakage at the ends. And more importantly, as the ocean warms, heat is seeping in under the ice sheet through ocean currents that's warming the bottom of these ice sheets and making them even thinner. So we might see a lot of this ice, which is on land today, become part of the ocean tomorrow. Well, if ice on land becomes part of the ocean tomorrow, sea level goes up. Sea level also goes up because the ocean is warming. So as the ocean warms, it expands, it occupies more volume, and sea level rises. This diagram on the right is just a chart showing sea level increasing just for the past couple of decades by a few inches. But here's the real consequence. You have places like Kiribati, which is out in the Western tropical Pacific, where whole entire islands are becoming uninhabitable because they are literally inundated at high tide every day. And you have people with water up to their necks have to find a new place to live. And finally, there might be some gotchas, things that we don't completely understand, but we're very worried about. So methane, I mentioned methane is one of the greenhouse gases. It also turns out to be a very powerful greenhouse gas. We don't talk about it as much as carbon dioxide because it's a much smaller concentration. We measure methane at about 1.9 parts per million versus 410 parts per million for carbon dioxide. So it's a much smaller concentration of gas, but it's a much more powerful energy. It has a much bigger effect on the energy balance of the atmosphere. And so what we're worried about is that there is methane tied up in this matrix that we call hydrates that we find along the ocean shelf. And so as the ocean warms, there's the potential for these marine hydrates and also hydrates that are sealed in the Arctic permafrost, that part of the soil which is full of ice all year round. As that ice melts, it may release some of these methane hydrates, and we would start to see a very big greenhouse gas reaction. And just to give you some numbers, 2006, we measured, or we estimated that there was about 3.8 million tons of methane that was released from permafrost. And just a decade, not even a decade later, that number had increased by almost a factor of 5. Also, I mentioned about the Antarctic ice sheet. So if the entire West Antarctic ice sheet, so Antarctica is essentially split down the middle by this, the Transantarctic mountain range. East Antarctica is a much larger ice sheet, is very stable, but the West Antarctic ice sheet is very unstable. It's flowing into these two seas, the Ross Sea and the Weddell Sea, and it has this very long, narrow peninsula that's full of ice. Well, the peninsula has been shedding its ice. You see in the newspaper about big icebergs that are breaking off of Antarctica. They're breaking off of this Antarctic peninsula here. And sometimes they're the size of Rhode Island. But more importantly, all of this ice that's tied up in West Antarctica is slowly oozing into the Southern Ocean. And it isn't getting replenished as fast as it's oozing out. So we're seeing a diminution of the West Antarctic ice sheet. And if all of that were to go away, we don't anticipate this anytime soon. It will take a century or two for this to happen, if it happens. But if it were to happen, it would raise sea level by 16 feet, not a few inches, but by 16 feet. So we would see hundreds of millions of people living along the coastlines of the planet who would no longer have a home because sea level has gone up by 16 feet. So what can we expect humans to do in the future? Well, one thing humans have been doing pretty inexorably since they appeared is grow in number. This is just the time series of population, and I've marked a few milestones here. The planet first achieved 1 billion humans in 1803. We gained our next billion in just about 130 years. We gained 2 more billion in only 40 more years. And we're due to double again in about a year or two. So human population is definitely growing. And along with the growing human population is the demand for energy. So part of that is because we're doing better at medicine. Part of that is because we're concentrating humans in cities. This is a fantastic statistic that the National Geographic puts out. But if you define a mega city as a city with 10 million residents, well, there are 3 such cities in 1975. There are 37 today. And there are 5 cities that have more than 30 million residents in a single city. And finally, the other thing that humans have been doing quite efficiently is concentrating wealth. So currently about 5% of humans are consuming about 23% of the energy. And we have major issues regarding inequality worldwide that feed right into the vulnerability to global climate change. Now, I put a little note here, COVID-19. I produced this slide based on data from the National Geographic a few years ago. And this past year, everybody's been talking and living through a pandemic. So will COVID-19 interrupt these trends? It's an interesting question, whether life expectancy will continue to rise and whether humans will continue to concentrate in cities. But more importantly, what we can expect humans to do is to continue to combust fossil fuels. And what's shown here is the emissions of carbon dioxide over the past couple of decades. And you see it rising from about 20 billion tons per year in 1990 to about 40 billion tons per year recently. And the question is, what happens after this vertical blue line? Where do we go from here? Well, what I've been calling the business as usual scenario is just continue growth as the human population grows, our energy consumption grows, and we continue to emit more and more carbon dioxide. And we go off this chart somewhere in the 2070 range, where we get to double the amount of emission in just a few decades. In 2015, there was a meeting of all of the countries of the world in Paris, and they achieved a landmark agreement that everybody calls, uncreatively, the Paris Agreement. But that agreement basically calls for all the countries made promises that they would curtail their increases in carbon dioxide emission. And so we would expect, if everybody keeps their promise until the end of the century, we would expect this horizontal blue line to prevail. We'd stay at about 40 billion tons of carbon dioxide every year. Well, if we do that, if we keep our promises as a world, as a community of 192 nations, there's still only an 8% chance that we're going to keep the planet from becoming 2 degrees warmer than it was in pre-industrial times. And our best estimate is that 2 degrees is something of a threshold when we reach a level of dangerous climate change. There's a dispute. There was a report that came out a couple of years ago arguing that it's actually 1.5 degrees. Well, 1.5 degrees is basically a done deal. It's already baked into the cake. So the trajectory we have to be on if we're going to avoid that kind of dangerous climate change is this kind of trajectory, where instead of keeping our promises to not get any more emissions out, we actually reduce our emissions. And in fact, some of these blue lines here, which are different scenarios, go to negative values, meaning we're not only emitting no carbon dioxide into the atmosphere, but we're pulling it out of the atmosphere using technologies that are currently available. So let's talk about Virginia. I mean, I said I was going to talk about Virginia, and I'm only just getting to it, but it's very important to think about what the global context is before we think about what's going to happen in Virginia. And the most important message is that Virginia is not exempt. It's part of the earth. And all of the things I've been talking about will prevail here in greater or in lesser ways. We're going to be having a new normal. And getting ourselves ready for that new normal is really what we have to do. So what does our new normal look like here in Virginia? Well, one thing, of course, it's global warming, and we're going to warm up. This is a projection. This happens to be from the business as usual scenario. The more likely scenario is less than this, but not by a lot. So here in Virginia, by about the middle of the century, just 3 decades from now, there will be 40 to 50 additional days every year when the average temperature of the whole day gets above 90 degrees Fahrenheit. 40 to 50 days. That's more than a month of additional days above 90. Now that sounds pretty bad, but you can contrast that with Yuma County, Arizona, which is expected to have an increase of 30 days, similar to our increase, of days over 100. And they will have nearly half a year of days over 90. So we anticipate that places like southwestern Arizona may become fairly inhospitable for humans. The other part of the new normal is flooding. We've seen this happening recently. Flash floods happen here, flash floods happen there. You may remember Ellicott City in Maryland had 2 500-year flash flood events back to back. Basically within 24 months of each other, they had 2 500-year events. The same thing is happening in Virginia. So here we had this event in August of last year, a deluge associated with a downpour. We had 5 inches of rain locally in the Leesburg area, and it produced creeks that overflowed their banks, cars running off the roadways, and so on. And we thought, wow, that was a pretty big event. 1 month later, Alexandria flooded, 6 inches of rain on the east side of the city, 5 inches of rain in Alexandria, backyards flooded, basements completely awash, the usual pictures and news crews out getting quotes from people saying, I never saw it rain so hard. Well, that's exactly what we expect to happen in this area in association with climate change. Hurricanes in Virginia, is that our new normal? Well, not necessarily. We do have data to show that tropical cyclones, which is the general class that hurricanes are in, tropical cyclones are gaining in intensity over time as a result of global warming. They're reaching farther north as a result of global warming, and they are moving more slowly. This one we're not entirely sure is due to global warming, but we do see slowing down. And of course, if a tropical storm slows down, that means it has more time to damage a local, a given place. So this is just one example, and I had this same picture on my title slide, Tropical Storm Isaias, that came up the east coast of the United States in 2020 and got all the way into Canada before it lost tropical storm strength. And of course, it raked over eastern Virginia and caused quite a lot of flooding. A lot of people think that tropical cyclones and hurricanes are wind events, which they are, but most of the damage comes from water, and it's primarily from flooding, and particularly here along the coastal zone of Virginia, where the ground is very flat. And once we get a lot of water, it's very hard to get rid of that water because it's got nowhere to go. But even if we don't have a tropical cyclone, and even if we don't have a downpour causing a flash flood, we can get situations like you see in this picture. This is from Norfolk in July of 2015, a beautiful sunny day, no rain in sight, hadn't rained for days. but it happened to be the high tide for the day and for the month, and the water was gushing up out of the storm sewers and flooding the streets. It flooded the campus of Old Dominion University and produced quite a lot of damage, just simply because sea level had risen so high that the water was no longer able to get out. Here's one article that appeared just a couple of years ago where they projected that something nearly 1,000 properties in Hampton Roads, which is near the mouth of the Chesapeake, could be underwater within a decade. And this report from NOAA just came out a couple of years ago, said that the flood that we see today in Norfolk will become a daily event by the 2060s. So this kind of a picture will happen every day unless we change the infrastructure that has to deal with stormwater. Norfolk is in a peculiar place because it has what I call a double whammy. So the one double whammy you already know about. When you warm up the ocean, it expands, occupies more volume, and its sea level goes up. And we have the other part of this double whammy is that when the planet warms, the ice that's on land, our ice sheets and our glaciers melt, and they also raise the sea level. But in addition to that, so we've already seen this picture, in addition to that, we have another double whammy, which is we happen to be in a place where the land is subsiding. The land is sinking because of what we call post-ice age rebound. And the other part of what's going on in Southern Virginia, near the mouth of the Chesapeake, is sediment compaction because we're withdrawing groundwater. The groundwater occupies volume as we irrigate, as we pull water out of the ground to irrigate. The sediment compacts and the land sinks. And so the post-glacial rebound is because about 20,000 years ago, North America was covered with a very thick, 3 kilometers thick sheet of ice. And that's why we call it the Ice Age. But here in Virginia, we were not covered by ice. And in fact, the ice had oozed out from the Arctic into North America and pushed the ground in front of it up. So you see the ground was elevated in front of where the ice sheet was moving 20,000 years ago. Well, as the ice sheet retreated, all of this land has been slowly subsiding back to where it was before. And so we get post-glacial rebound where the ground is actually rising in New England and sinking in Virginia. Groundwater withdrawal, these are just 2 places where there's an enormous amount of groundwater withdrawal when measured in feet of groundwater level change. 50 feet here at this place called West Point near the Chesapeake mouth, and this other place called Franklin, both in Virginia. Tens of feet of groundwater withdrawal resulting in land subsidence of several inches. So the double whammy produces this interesting data point. If we measure sea level at Sewell's Point, which is down at the mouth of the Chesapeake, that has just in the past 90 years has increased by ½ a meter, about 20 inches of sea level rise. That's about twice as fast as the global rate of change. So because global warming is going in the same direction as these other things that are happening as a result of completely not global warming, we see issues in Southern Virginia. Now, global warming is what Daniel Kahneman, who was a Nobel laureate in economics, referred to as a perfect problem. And here's a couple of the characteristics of global warming that make it a perfect problem. First of all, it's remote. Here in Virginia, the population is by and large wealthy in comparison to the global average. And so we're more resilient, we're more capable of dealing with minor inconveniences or changes to a new normal. The bigger effects are going to be happening to people who are far away. So you could take the attitude, why should we care? Also, we know that these changes are happening everywhere. There's no single place where we can concentrate resources to fix it. It's very slow. The impacts occur gradually. There's no deadline for getting a solution in place. Well, the sea level is rising very slowly, so what? We'll have another decade or 2 before we have to worry about it. It's painful. It requires big sacrifices now in order to avoid uncertain losses far in the future. It's complicated. There's no single cause. There's no single solution. There's no obvious single enemy. We can't send the Marines to fight global warming. And it's controversial because, as any science, there are error bars on all of the things that we are estimating and predicting. And there are people and private companies that have an interest in not doing anything because they're profiting from the way things are today. So change is bad. And also quote this guy, because Jonas Salk is on everybody's mind these days because we're talking about a global vaccine for the current pandemic. And of course, he was a developer of the successful vaccine for the pandemic of the mid-20th century, poliomyelitis. He has this interesting question. He says, the most important question we must ask ourselves is, are we being good ancestors? So think about what the earth is going to be like for your children who will live into late this century, and your grandchildren who will live into the next century, and your great-grandchildren who may live into the century after that. How will the earth appear to them because of what we're doing today? So there is hope. There's a lot of cities who are forming climate action plans. In fact, Chicago, as one example, had a climate action plan all the way back in 2009. And a number of other cities are adopting climate action plans where they're thinking about how to both adapt and mitigate. I mentioned Fairfax here. That's actually Fairfax, California. It's not our Fairfax, but our Fairfax is in the process of developing a climate action plan. And Alexandria already has an Eco-City Alexandria plan, which is about to get renewed. When we think about how to deal with climate change, there's two strategies. First is adaptation. So we know there's going to be a new normal, and we have to prepare for it. We have to increase the resilience of our communities in order to be able to withstand the changes that we're inevitably going to have to face. And so what we do is we have to assess what we have that's at risk. We have to assess what's the likelihood of bad stuff happening to our assets. And then I have this very lame phrase here, there's no I in team, but there's 3 I's in adaptation. And of course, not in the word itself, but we can ensure ourselves by spreading the risk, we can strengthen our infrastructure, and we can provide incentives for people to do the right thing. The other strategy is called mitigation. And there, when instead of accepting the inevitable, we try to change what the future looks like. And the way we can do that is not rocket science. It's not even geophysical fluid dynamics. It's simply reduce the concentration of the greenhouse gases, carbon dioxide and methane, in the atmosphere. And there are 3 ways we can do that. One is conservation. We can use fewer processes that emit carbon dioxide and methane. That will reduce our emissions and over time reduce concentrations. We can also use alternative energy sources that don't rely on fossil fuels. That will likewise reduce our emissions. And finally, we're now in the process of developing technology that will allow us to not only stop emitting, but gather carbon dioxide out of the atmosphere and fix it into mineral form so it's no longer participating in the energy imbalance. Well, in Virginia, conservation is a tough problem because there's no single place to start. This is how we consume energy. This is data from 2017. And you see it's about equally split between residential, commercial, industrial, and transportation. So you can't say just get all the cars off the road. That'll only solve about 30% of the problem. So it has to be an all or nothing, an all of the above type strategy where we think about all of the ways that we're consuming energy and generating carbon dioxide. Fossil fuel is important to Virginia's economy. So it is going to be painful here in the Commonwealth to get ourselves off the fix of fossil fuels. At the end of 2017, Virginia was the 3rd largest state in the country in proven coal bed methane reserves. So if we're not going to use methane, all of that has to stay in the ground. And therefore, any profits we might reap from getting it out of the ground and burning it cannot be realized. Also, in Norfolk, the port happens to be the largest export center for coal in the United States. So again, coal that we're not necessarily burning locally, but we are selling overseas is coming from right here in Virginia. Now it can be done. So this is a cool diagram. It's probably a little impenetrable the way it's displayed here, but if you just look at the words, over the past decade, Virginia has converted from essentially a coal burning power plant economy. 25% of our electricity generation was by burning coal. That's gone down to 1% in just 10 years. And natural gas has doubled, almost doubled, from 33 to 56%. That's because of the price. The price of natural gas dropped like a stone through water because of the new technology, fracking, where we fracture the rocks and get the gas out from underground. That made natural gas so cheap that it was outstripping coal as a cheap fuel. And all of the power plants converted from coal to natural gas. So the result has been that we have very rapidly converted from coal to natural gas. Now, natural gas is about half as potent at producing greenhouse gas emissions as burning coal. So that's a step in the right direction, but it's not where we need to be. Where we need to be is down here in renewables, hydro, nuclear, and wind and solar, and because they are non-emitting. And so particularly with renewables, where we don't have as much of an issue with regard to the waste products that we have with nuclear. Wind power is abundant. If you put windmills up on the Blue Ridge, you will have an abundant source of wind. Solar is abundant, and right now is a great time for homeowners to be getting involved in solar because there are tax credits in place and they've been extended through 2022 at the federal level. So it's actually relatively cost effective to switch your home power production to solar. And of course, at a commercial scale, solar is something that everybody is looking at. Lots of companies are looking at it, and lots of utilities and so on. Virginia is taking action. So if you go look back about a decade, Governor Tim Kaine formed the Climate Change Commission, and commission produced a report about how Virginia was vulnerable to climate change and what steps the Commonwealth ought to be taking. A few years later, Governor McAuliffe reinvigorated the Climate Change Commission, and they produced a report that said, guess what? We are still just as vulnerable, if not more so, than we were a decade ago, and we need to do something about it. In 2020, two very major pieces of legislation were passed and signed into law by Governor Northam: the Virginia Clean Economy Act, which pledges to make Virginia 100% renewable on electricity generation by the middle of the century, and the Clean Energy and Community Flood Preparedness Act, which, among other things, will put Virginia together with several of the northeastern states in the United States as part of this regional greenhouse gas initiative, which is an emissions allowance auction. So it's a way to trade in an economic market setting how much emissions are taking place. And by ratcheting up the price over time, we ratchet down the amount of emissions that can happen. Other things we can do, we can redesign our cities. If we have a couple of decades, there's plenty of time to think about how to design our cities so they're more climate friendly. And that's not just about painting roofs white, which is one of the things we can do, but changing the way we pave our streets, changing the way we build our buildings so that they're more conservative in terms of energy use, change the way we practice agriculture so that we're no longer losing carbon dioxide in the atmosphere, but also that we're conserving topsoil, we're reducing pollution, and we're generally helping the planet in ways other than just greenhouse gas warming. We can, of course, conserve energy as we have done in the past. When there were oil embargoes, everybody put on a sweater, but there's plenty of other ways that we can envision at the large scale conserving energy. And of course, start thinking about ways to generate energy and store it that's a non-fossil fuel source. I'm just going to draw your attention to this website. It's called drawdown.org, where they're literally publishing hundreds of solutions that individuals, communities, and large corporations can take to start drawing down the volume, the concentration of carbon dioxide and methane in the atmosphere. So let me finish. We know that climate is changing. This is a fact. It's not a theory. It's not a hypothesis. It's happening. And furthermore, it's happening at a pace that we have not been able to, we haven't seen in literally millions of years. We also know that humans are mostly responsible. There are other factors, of course, but if you look at the data since about the middle of the 20th century, it's us. Our planet, our nation, and the Commonwealth are facing unprecedented challenges. The COVID pandemic is an unprecedented challenge we haven't seen for 100 years. The climate change is an unprecedented challenge we have never seen as a species, and we must address it soon. Being prepared for the new normal requires that we understand what that new normal is, why it's happening, where it's happening, how much it's going to happen, and where the vulnerable assets are. where are our communities going to have the hardest time? Where are the challenges the largest? And of course, you can guess that's going to be in our underprivileged communities, where resilience to climate change is not job number one, but putting food on the table or getting a good job is. So there is hope. We can envision a sustainable future in which we adapt to the new normal. And we can mitigate the even bigger adverse changes that we expect in the future. So I'll be happy to take any questions.
Thank you so much. What do you think the geographic migration pattern is going to be? Are we going to be moving to Antarctica? Are we going to have everybody move away from the coast into the center? And are we going to be climbing Mount Everest with no snow on it? What's the future going to be like? So, if you were a real estate investor, where would you invest?
Well, I'm not Lex Luthor, so I'm not going to propose a nuclear weapon in the desert of Nevada. But no, it's a great question. So, I mean, a lot of it comes down to costs and benefits. So think about the coast. The coastline is a place where we have invested enormously. We have a lot of big communities on the coast. We have a lot of beautiful tourist attractions on the coast. As the sea comes up, as the sea level rises, we have two choices. We can abandon those places. We can abandon New Orleans. We can abandon Manhattan. We can abandon Alexandria, or we can fortify infrastructure changes to be able to get rid of the stormwater as it accumulates, protect ourselves from the sea as it's encroaching on the coastline. Those are very, very, very expensive solutions, but we may deem the value of having Manhattan or the value of having New Orleans as higher than the cost of building all that new infrastructure. Another interesting fact about how we expect climate to change in the future, a lot of our food in the United States is produced in the center of the country. The center of the country is a relatively dry place, and we expect it to get a lot drier with climate change. So as I said, it's a complicated story. In some places it gets a lot wetter, and in some places it gets a lot drier. Well, we expect it to get a lot drier in the center of the country, also in the Caribbean, also in Mexico. And so there may be some migrations away from those places because it no longer will be necessarily all that feasible to grow grain. And we may have to annex Canada in order to be able to grow our grain. I'm not saying we should do that, by the way. So you will see that. One of the things that the US military, the Pentagon, is very concerned about is climate refugee migrations. So if you think about places where coping with sea level rise or with unbearable heat waves, in places where they don't have air conditioning, they don't have the money to build a seawall. Those are places where you'll see large populations migrate away, and they may cross national borders. And then there will be a crisis of, military crisis. And our military, the US military, is envisioning how they're going to respond if there are either humanitarian crises associated with climate events or conflicts associated with climate refugees encroaching across the border into their neighboring country. Think India and Pakistan, and you'll understand what I'm talking about.
Thank you. We have a couple of questions in the chat box. Here's one from Ruth. She says, I live in Montana, North Dakota area. We have approximately one oil rig per 3.5 miles, all of them burning off methane. I saw the same thing when I went to Oklahoma a couple of weeks ago. Why aren't we collecting it? We're in the second year of a drought, perhaps caused by global warming. I know that President Biden announced this needs to be addressed. Thank you.
Yes, it's a great question. So between gas leaking out of pipelines and methane that's just being flamed from oil rigs and from gas drills, natural gas wells, we have an enormous amount of wastage and emission that's going on. And the only reason why that's happening is because of cost. Today, it is cheaper to just let it all go than to collect it and reuse it. But as you saw, cost can be a very strong incentive for change of behavior. And just here in Virginia, we've seen this changeover from coal to natural gas because of the price of coal and the price of natural gas. And they flip-flopped which one was cheaper, and boom, we switched. So you'll see that same kind of a thing happening if the market changes the price to a level where it becomes economical to capture all of that methane. So you will see it. It will happen at some point. But I think an interesting thing about that part of the world, the Northern Great Plains, is it's a very windy place. And it's very economical to put up farms of windmills to capture, to generate energy from the wind that's blowing there. And in fact, places like Wyoming, this is a big business now. If you go to Wyoming and just drive across the Continental Divide, you'll see as far as the eye can see windmills turning, and there's money being made from all of that churning of windmills. So I mean, it's at some level, it's all about the economics. I think that was a Bill Clinton line. It's the economy, stupid. So you can imagine that as the economy evolves, it needs to have incentives for these things to change. But once the change starts, it's like a ball rolling down the hill, and you'll start to see these changes happening on their own because business people are savvy and they'll follow where the profits go.
Thank you. Yes, and then it has a trickle-down effect on the coal miners, right? So now they're unemployed. So we have to think forward to help support new developments and innovation.
Exactly. So I mentioned about underprivileged communities here in Virginia. We have a big swath of the state is in Appalachia. It's a lot of coal mining territory. It's also uranium mining, by the way. And those are communities that will be hard pressed to make transitions. So there's going to have to be government support to figure out how to incentivize those communities to switch over from what has been their cash crop, digging coal out of the ground, for so many decades, so many generations.
Here's another question that's related. What are your thoughts on carbon tax and dividend legislation as a mitigation effort?
Yeah, that's a great question. And sadly, I mean, that was the one part of the talk that I removed because of time consideration. But it is an excellent approach. It's related to this regional greenhouse gas initiative that I mentioned that Virginia has just joined as of last year, where you create a market and you apply a price for emitting carbon. And then it's frequently called a cap and trade market, where you cap the total amount of emissions that can happen. And then people trade. Those people who need to emit will trade permission to emit. From those who don't need to emit very much will sell their permissions to those who do need to emit a lot. Another way to do it is to impose a tax, where if you emit above a certain level, you have to pay per ton of carbon. And then that money is used to build resilience in the communities that aren't able to cope with climate change. So those are both really valid ways to do it. As it turns out, there's a lot of detail in the way it gets executed. So they did a cap and trade market in Europe for the past decade or so. And it really didn't work at the beginning. They set the price too low, and there were a number of other bureaucratic issues with it. So it almost failed. But meanwhile, in California, you have cap and trade market that's doing very well. So it all kind of comes down to execution. But those are excellent strategies. And I'm sorry I didn't get a chance to mention it.
So we have at least 3 more questions. I hope we can get to them all. Here's one from Lori. Given the greater amount of rainfall, subsidence, or sea level rise, how concerned should Virginians be about vector-borne diseases like Zika, West Nile, as we get wetter and wetter?
That's a good question.
That's a great question. So the thing I'm most worried about is ticks and Lyme disease, because if you look at the data, the big problem that we've been facing as a result of global warming in this area is that the winters are not as harsh as they used to be. And it's the really harsh winters with long periods of sub-zero, of sub-freezing temperatures that sort of whack back the tick population. When you don't have a winter that has a couple of weeks of sub-freezing weather, the tick population propagates. And basically from generation to generation, year to year, you get an explosion in the tick population. Of course, the ticks have Lyme disease, so that's an issue. The question about those other vector-borne diseases you mentioned, I mean, we used to have cholera in this area. We used to have malaria in this area. If you go back to the 18th and 19th centuries, And so it's always possible that could come back here. But in general, our public health and our other systems are able to cope with it. So I don't see that as big an issue in this area, but it is a concern. And as we get warmer and wetter in Virginia, then those things could become issues.
Thank you. Here's one from a Mason student. I am a student at Mason, and I am originally from the Texas Gulf of Mexico area. We've seen a huge increase in hurricanes over the last 10 years. What can we expect to see if this climate change increase carries on at this pace?
Yeah, so there's a couple of important details there. When you see hurricanes coming ashore, you're only seeing the tail end of a storm. That's a storm that has been at sea for maybe days or weeks. And so it's the landfall that we pay attention to, because that's when it causes damage to human settlements. But in fact, it's been out at sea for a long time. And what we're seeing is that tropical cyclones at sea are getting more intense with time. And that's just because their main energy source is the ocean temperature, sort of the energy that's contained in the upper few meters of the ocean. So as the ocean warms up and that layer of warm water near the surface deepens, the energy source for hurricanes gets much, much bigger. And so hurricanes have the potential to reach a much higher level of intensity. So you see more category 3, 4, and 5 storms. Now, whether they make landfall or not is almost an accident. There's no clear indication that landfalls are going to change in terms of where we're going to see landfalls. Are going to see more landfalls? Is Texas going to become more prone? But if you just adopt the view that landfalls are going to be about the same statistically, so that roughly the same number of storms are going to hit any given stretch of coastline in a given decade, but they're all going to be more intense, or many of them are going to be more intense. So the damage and the flooding is likely to be worse. We saw this in Houston, when Houston got 50 inches of rain with the tropical cyclone that hit there a few years ago, Harvey. So, and this year we saw a record number of storms, but importantly, almost all the ones that made landfall in the US made landfall in southwestern Louisiana. So that if you notice, there were 6 storms that came ashore just west of New Orleans. So the beauty of that is it's split. It's like in bowling, where they couldn't get the spare. There was New Orleans to the east and Houston to the west, and the storms all split the difference between the two and went through much lower populated parts of Louisiana. Had those storms veered 50 miles east or west of their actual course, they would have affected millions of people. And of course, the people who were in the path of those storms suffered mightily, but we really dodged many bullets of tropical cyclones coming ashore in the Gulf of Mexico this year. There's no reason to believe that they couldn't have gone to New Orleans, or they couldn't have gone to Houston. And so we might have seen a much bigger issue. And in the years in the future, if they're all going to be a lot more intense, we expect that that kind of damage is eventually it's going to hit the big population centers.
Here's one. This is a wonderful talk, which we all agree. Should humans focus on carbon capture technology to convert atmospheric CO2 to some mineral form and bury it under the ground, or transition to alternative renewable energy sources?
So it's a great question, and it's difficult to answer, because today that carbon capture and sequestration technology is quite young, quite immature. We're able to do that. Basically, the idea is you blow a fan to drive air through a filter, and the filter captures the carbon dioxide by forming it into a mineral. Basically, it has a chemical reaction with materials that are inside the filter, and it produces a mineral. And then you can take that mineral and bury it in an abandoned salt mine or wherever it won't have access to the atmosphere for hundreds of years. The problem is that we can only do that in really small batches. And remember, the emission of carbon dioxide worldwide today is 40 billion tons. So that's 40 trillion kilograms of carbon dioxide. That's a big number. It's a number 4 with a lot of zeros after it. And we're able to capture and sequester 4 with just a couple of zeros after it. So the question that is everybody is working on who's in that area is how well can we scale up this technology of carbon capture and sequestration? And it's an open question whether we're going to be able to do it. So you really can't bet on that at this point. And you certainly can't bet on it as a singular solution. So you have to have what I described as an all of the above strategy, where you work on renewables, you work on carbon sequestration, you have a carbon tax to provide incentives, or a carbon trade economy so that you provide incentives for people to stop emitting, and you conserve, and you fix your cities, and et cetera, et cetera, et cetera. So you have to do all of those things. You can't simply say, oh, we'll have the technology, it'll be fine, in another decade we'll just be sucking the carbon dioxide out of the atmosphere. That's not a strategy that's high probability of success.
Here's another question. This is one that we all should be interested in. What changes can students or families do to begin to implement in their daily lives to assist with lowering their ecological footprint? And what can corporations do about it?
So it's very common for people to say, I'm solving the climate change problem. I changed all the light bulbs in my house to compact fluorescence. And that's true, it's helping, but it's a fairly tiny thing, because the same individual then got in her car and drove 20 miles to work. So what I tell people is they need to be doing two things if they're taking climate change seriously. One is look for ways to reduce your own personal carbon footprint. And you can do some of that. I mean, a typical American consumes at least 4 times as much energy as the average human on the planet. And if you compare the average American to the average citizen in underdeveloped countries, that's more like a factor of 10 or 20. So clearly there's ways that we can do better at consuming less energy. But I think as important, or perhaps even more important, students and all the rest of us can become activists. They have to tell the people who make decisions at the large scale, their representatives in their municipal government, in their county government, in Congress, in the state legislature, tell those people that they demand new regulations, new policies, new laws that will incentivize the reduction of carbon dioxide emissions. And that's when you're going to see the biggest bang for your buck. If you spend your time, and it doesn't have to be all your time, it can be a small portion of your time, but if you spend your time actively seeking to get the people who have control of large scale things, to get them to make the changes in policy that will drive the whole society in the right direction, that will have a much bigger impact. As far as corporations go, the corporations are largely driven by, well, they're driven by profit. So it's mostly a question about how that balance between profit and loss is going to flip between a fossil fuel-based economy and a renewable energy-based economy, or conservation versus consumption. And really, that's a balance which isn't terribly far off. And we only need a little bit to flip it, but it's not for individuals to be doing that unless they happen to be CEOs of large corporations. It's for collective community action to help those companies, get incentivized to change their behavior.
Thank you. Here's a question, and it will be interesting to see if Mason supports this idea as well as a lot of corporations. From David, I think one positive outcome of the past year's pandemic is that employers are more open to remote work, so that a person can avoid having to drive 20 miles to work, and that 20 miles may translate to an hour or 2 on the road. So it's not just the distance, it's how long the car is going, right? What do you
Absolutely.
think?
Yeah, so like I said, I put a little asterisk or a little arrow in one of my slides about the concentration of human population in cities. That's been happening for the last century or more, but maybe it's over. And I am not a social scientist, so I can't say one way or another whether it's true. But that will have two effects. One is, there'll be a lot more telework, like the questioner is mentioning, David, I guess, is mentioning. But it also means that, people will be living at, farther away from population centers, and that means farther away from services. So they're more likely to actually get in their car just to go buy groceries or do the little things that they might like to do. So it's not entirely clear whether, advancing telework is going to be good or bad for climate change purposes. Certainly will cut down on people commuting to their offices if they live in the suburbs now, but it may cause more people to want to live in the suburbs. And so you wouldn't necessarily get the effect you like. So it'll be interesting to watch to see how this all plays out. It's not entirely clear, if we're able to defeat the pandemic in a timely manner soon, then a lot of the changes we've seen over the past year may revert to the way things were, status quo ante. But chances are that we've learned how to do things in a different way, and so some of these changes might stick. And I'm interested to see how it's all going to play out, but it's certainly not my level, my area of expertise.
So one thing that you mentioned corresponds to some of the increasing global in greenhouse gases is deforestation. Are planting more trees helpful? And is it, does it have to be on a massive scale, or does planting some trees in our yard, our neighborhood, our school grounds help?
It definitely helps. And I don't have numbers. I think somewhere in many of the slides down below, I have numbers of how much carbon you can actually expect to keep out of the atmosphere by planting a tree. It's all about the growth time. So as a tree is growing, it's fixing carbon in stems and trunks. And after it has become mature, then it's basically, if it's a deciduous tree, it's giving up its carbon in the fall and it's refixing its carbon in the spring. And there's really very little change over the course of a whole year from a mature tree. So we kind of have to keep harvesting mature trees and planting new trees. And that's kind of a large scale thing rather than it's great if people plant trees in their backyard. That's fantastic. And it certainly helps. But what you get in terms of a longer term benefit is if you're recycling, if you're harvesting and replanting new trees all the time. And that would actually give us quite a large scale effect.
I think that we've covered all of the wonderful questions from our audience. We want to thank you for starting off this Earth Month celebration for us. It gives us so many things to think about and wonderful things to start on and do, and especially write those letters, contact the people that can make the changes and be the change, right? Great. So thank you so much, Jim.
Well, thank you, Andrea, and thanks to everybody who stuck around all this time. It was a great pleasure.
Great, thank you. And we will post a recording of Dr. Kinter's talk on the Galileo Science Cafe website. Thank you, guys. Have a good weekend. Bye-bye.
Bye.